Hello everyone. Today I am going to explain GROOD, gradient error out of distribution detection, which was recently accepted in TMLR. And in this project I have enjoyed working with Sabi, Yan, Paul, and Liam. Now let's start to talk about the agenda. So first I will introduce the problem of out of distribution detection, then I will talk about GROOD, and then we'll show a toy dataset showing the dynamics of GROOD, then the main results, and the conclusion. So first, why do we care about OD detection, or what is the problem of out-of-distribution detection? Assume you have a model that has been trained on cats and dogs, and you give it a different image. So the model needs to know its own knowledge. It should be able to say, okay, I don't know what is that here. So for example, if you give it an image of cat or dog, the model will be able to generalize and classify nicely. But what if you give it something out of distribution like a bird? What will be the output? So it will be completely random based on the features or spurious features in that input image. And any OOD detection method tries to predict whether that input is in distribution or should we reject that prediction. It is not safe to do that prediction, especially in a deployed model. So what are the existing methods to detect OOD in a fast manner? So we have the classification base that work post hoc on longest, softmax, energy scores. We have a different family of methods that works by getting exposed to OOD data during the training, like outlier exposure. You have the density based, where you fit your in distribution representation with a probabilistic model. You have a distance based, in which you assume the OOD data should be far away from your in distribution data. We have reconstruction based, where you train, let's say, an autoencoder on in distribution data, and you compute the reconstruction loss during inference. If the model is able to reconstruct nicely that image, most likely it's in distribution. If it is something new, most likely it will fail to reconstruct. So what are the OOD types that we have? We have two types. Covariate shift, where the input space is shifting, like for example, you have real images, cartoon, sketches. And the second type is the semantic shift, where your label space is shifting, dog, cat, and fish. Now let's assume you have a model that has been trained on dog, cat, and fish, and during inference you give it bird and car. So you expect the model to reject those two predictions, and that is the mission of OOD detection methods. In the covariate shift, your ultimate goal would be to generalize. Like, for example, your model has been trained on real images of dogs. Your ultimate goal would be that it would generalize and say, okay, this is a dog, but in a cartoon format or in a sketch format. The main focus in OOD detection is the semantic shift, and that is what GROOD will focus on. So now let's explain what is GROOD and how it works in the gradient space. So to summarize our method, let's assume you have two input images, the line, the red arrow, the dog in green arrow, and you have a model that has been trained on cats and dogs. And this is the feature extractor to an ultimate layer, and you have two prototypes. And you have the feature representation H. We start by constructing distance of input to in distribution prototypes. And now, for now, let's assume you have an OOD prototype as a reference point. So if we compute the cross entropy loss of these distances using the pseudo label as our ground truth with respect to the OOD prototype, then we will have different gradient statistics for in distribution data versus OOD data. Like for example, for in distribution data, in order to increase the confidence on the predicted class, we will need like minor changes to that OOD prototype. We won't care about it. But for an OOD data to improve its in distribution confidence score, we will need to push or make major changes to that reference point. And then we'll have a higher gradient value for that. So the in distribution prototypes are just simply computed as a running mean of your in distribution representation. And we have the distance to class prototypes. Okay, so now let's talk about the gradient computation. How do we compute the gradients? So logits will be as negative distances to in distribution and out of distribution prototypes, which means if you have a higher distance, its logit value should be lower. And our loss function, we use the standard cross entropy loss on those distances, treating them as input logits. And a closed form of our gradient with respect to that OOD reference point will be something like the direction and magnitude. So your magnitude will come from the softmax probability distance of that OOD prototype, and this is the direction. In that case, it will give you richer information than just using the gradients with respect to the model weights or using this just the distance to the feature space. So the gradient dynamics, so in this Disney plot, we have plotted the gradients computed with respect to the noise prototype. And as we can see that in distribution data are nicely clustered, and OOD data, the model is able to reject the OOD data in the representation space. Okay, so now let's talk about the OOD score itself. So after computing the gradients, we have two options, either using the norm of the gradients or indexing your training data gradients and using k nearest neighbor, like what is the nearest neighbor to that gradient space in distribution data. And that is what we are using. So it tells us how different new sample gradients from the gradients of the samples the model was trained on. So we compute minimum distance like a nearest neighbor. So if we have a small distance, a low score, the gradient is similar to the training data, likely in distribution. If it has a high score, larger distance, the gradient is far from any training data. Most likely it's out of distribution. So what is the intuition behind GROOD, or what gave us that idea? So you have neural collapse inside in distribution data aligns with near class prototypes as per Papian paper. And the OOD prototypes, the concept OOD data clusters are scattered. And that is why we define an OOD prototype as just the reference point that will be used during the gradient computation. Gradient-based differentiation. So we measure the effect of an OOD prototype perturbation. What will happen if we perturb the OOD prototype to the prediction using distances? Will it improve the in-distribution confidence score, or will it destroy it? So let's come to the question, how do we compute that OOD prototype? So the key challenge in creating reference points for out-of-distribution data is that we don't have access to actual OOD data or access to a test OOD data. So we need to synthesize that OOD prototype, or we can use a simple validation OOD data. But for now, let's talk about synthesizing hard examples. So this method uses manifold mix-up to create features that lie on the decision boundary. So we use, let's say, the second layer output representation, and then we do a mix-up between the representation of the input image and the representation of second predicted class. So if the model has predicted, let's say it was trained on dog, cat, and fish, and it has predicted for that input image dog and cat as the top probability scores, we do a manifold mix-up with the second top class, and we do it as at an early layer. And then we get the penultimate layer output, and we take the average using just in-distribution data. So using the in-distribution data, and we mix it up with second top class for each instance, like each input data point. And then we get a nice reference point as an OOD. We have also tried multiple different methods to generate the OOD prototype. We have the synthetic OOD using manifold mix-up method. We have another idea of just corrupting in distribution data, like using adversarial attack, and using open OOD validation. If you have real data, definitely that is your best case scenario. or using just simple uniform noise, or using the mean of in-distribution prototypes. But so far, the synthetic OOD generation method is the best method without having access to unseen OOD data or test OOD data. Now let's talk about our toy dataset. So we have generated like 2D blobs. We have class 0, class 1, and class 2, these three classes as in distribution data. We have the orange part is the near OOD, and we have the red part is the far OOD. So now let's take a look at the evolution of the OOD prototype during the training if we do that synthetic idea. So at the start of the training, the OOD prototype was here, and the model was struggling to learn representation. Now it was able to disentangle in distribution data from OOD data, and as you can see, the OOD prototype is not supposed to be near your OOD data. It acts just as a reference point when we take the gradients to be able to say, oh, this has the characteristics of an in distribution data, or this has the characteristic of out of distribution data. So if we take the Disney plots of in distribution data versus OOD data gradients, we'll see that it was able to disentangle them. If we take the mean and variance of just the gradient norms, we'll notice that the norm of OOD data is much higher than in distribution data. Now let's talk about the main results of the paper. So GROOD was able to achieve decent results. In this plot, we are trying to show the difference between NINCO, which is near OOD data for ImageNet dataset, and OpenImage, which is for OOD. And on both benchmarks, GROOD was able to achieve decent results compared to existing methods. So this is our main table, and GROOD on CFAR10 is achieving near state-of-the-art results. FAR OD on CFAR 100 near and far, it had decent results. Also on ImageNet 200, it has a runner-up results compared to the best method. And same for ImageNet on near and far OD. So another good point of our method is the robustness to the checkpoint choice. Like for example, if you do early stopping and you stopped at epoch 90 or epoch 80, some of the methods will have like a not robust result. It will have higher standard deviation on near OD or far OD. So we tested the last 15 epochs on CFAR 100 to see what will be the standard deviation, and GROOD managed to have a low standard deviation. Even we can see that in the plots in terms of the AROC score at different checkpoints, and in terms of the standard deviation value of far OD versus near OD. So to conclude what we have explained so far, so GROOD is a novel OD detection method, and it leverages gradient information and distance metrics. So in our methodology, we leverage the neural collapse property in terms of in distribution prototype distances, and to have an OOD reference point, and we have a gradient based loss that is able to disentangle in distribution versus out of distribution. And in terms of results, it has been effective for near and far OOD samples and for different architectures. So, and it has an impact. So it tries to increase the reliability and safety in real-world DNN applications. Thank you. And the code for this paper is available at this repository. And the paper itself is at open review. Feel free to check it out. Thank you.